The metal wasn't weak. It was tired. There's a difference, and it has a record. A part can carry a load too big to break at once, and then die from the same small load repeated. This is the file on how that happens. First, what fatigue has cost. The de Havilland Comet, 1954, 2 jets lost to it, 56 souls. Aloha 243, 1988, 1 crew member, 65 injured. We begin here, quietly, because every drawing in this catalog begins with what it cost. Now the part, working. A steel bar with a single hole, carrying a load it was built for. Pull it once, hard, it holds, with margin to spare. By every static number on the drawing, this part is safe. Hold that thought. If you'd rather understand why things break than watch them break, subscribe. A new failure is drawn here every week. Now, the load does not come once. It comes again and again, and the part keeps a count we cannot see. Here is the flaw, and it is not a defect. It is the corner. At the hole, the load cannot flow straight. It must crowd around the edge. The stress there is several times the average across the bar. Engineers call it a stress concentration. The sharper the corner, the higher it climbs. This is where the crack will start, on the surface, at the riser. Each pulse of the load works the metal at that corner a little. Slip bands form. A microcrack opens. From here on, every cycle does something. It pushes the crack forward, a hair at a time. Watch the counter, not the crack. The crack you can barely see. With every cycle, the red advances a hair and leaves a ring behind it, a beach mark, one for each push. The part still looks perfect. The sound metal beside the crack still carries the load. The count is the only honest witness. There is a curve that governs all of this. Higher stress, fewer cycles, lower stress, more, until for many steels, a line below which the part runs forever, the endurance limit. But aircraft aluminum has no such mercy. It tires at any stress, which is why planes are not built forever. They are built to be watched. And then the last cycle. The crack has eaten so far across the bar that the metal still standing can no longer hold even the ordinary load. There is no warning in that final pull. What grew for 1,000,000 cycles finishes in 1. The same line is in the file 3 times over. The Liberty ships, whose welded hulls cracked at square hatch corners, one even split at the dock. The Comet lost at the corner of a fuselage cutout, where the stress ran far higher than anyone had drawn. The Comet gave us the proof. They sank a whole fuselage in a tank and pressurized it, over and over, a flight at a time. After 3,057 cycles, it tore, at a corner, exactly as the math feared. Fatigue stopped being a theory. It became a number you could test for. And the hardest lesson in 1988. A worn airliner had not one crack, but many, side by side along a riveted seam, each too small to fail alone. They linked, multiple site damage. The design that was meant to catch a single crack never planned for a row of them. So here is why yours holds. We stopped pretending metal never tires. Build more than one path for the load, so a single crack is caught and stopped. Assume the crack is already there and prove it grows slower than we inspect. Then go looking, with dye, with sound, with current, and find it while it is still a hair. Failure mode, fatigue. Not a weak part, a tired one, counting cycles no one watched. Nothing breaks without a reason. Now you know this one. Drawing filed. Like and subscribe to support the channel.